Buenos días a todos. Les queremos dar una bienvenida al simposio, al quinto simposio de Quiralidad. Aún, como ustedes pueden ver en el programa que está en la página, que ahorita se las voy a presentar, vamos a empezar a las 9:15 con la inauguración de este coloquio. Ahorita a las 9 estamos empezando, bueno, 9:08 estamos empezando la transmisión. Solamente les queremos decir que oficialmente empezamos 9:15. Les damos la bienvenida, agradecemos que estén aquí. Les voy a explicar un poquito cómo es la dinámica del día de hoy para las presentaciones que ustedes van a estar viendo. Voy a compartir mi pantalla para esto. Están viendo ustedes ahorita en la pantalla la página donde estamos alojando la información del simposio. Ustedes pueden ver aquí en letras azules que dice sigue la transmisión en vivo. Si ustedes aprietan este vínculo, van a poder estar yéndose a las transmisiones en vivo de YouTube. De cualquier modo también, aquí abajo en donde está el programa, ustedes, si ven, está activo un hipervínculo. Si ustedes aprietan, por ejemplo, en nuestra primera conferencia que vamos a tener de la doctora Cornelia Meitner, si ustedes aprietan en el título, van a poder acceder al resumen de su plática. Y si ustedes aprietan sobre el nombre, no lo voy a hacer para no generar un as ahorita donde yo estoy hablando. Si aprietan ustedes aquí en el nombre, los va a mandar, bueno, lo voy a intentar, los va a mandar aquí al canal de YouTube,
Si
en donde,
ustedes
en donde van a estar,
aprietan, por ejemplo,
en donde ustedes van a estar viendo la transmisión en vivo de cada uno de los ponentes. Están habilitados aquí los hipervínculos, de tal modo que cada vez que termine una plática, van a poder estar, bueno, se va a desactivar ese vínculo para la transmisión en vivo y van a tener que acceder al siguiente. Ya están todos los hipervínculos creados para que ustedes puedan estar accediendo a las diferentes pláticas que vamos a tener el día de hoy. Como les menciono de nuevo, la, la inauguración va a iniciar a las 9:15 por parte de la doctora Sandra Ramírez. Ahorita solamente quiero emplear estos 2, 3 minutos solamente para recordar que estas pláticas iniciaron hace 3 años por invitación inicialmente del doctor Germinal Cocho Gil del Instituto de Física. La primera reunión se llevó a cabo en el año 2018 y a partir del año 2018 hemos estado, bueno, ese mismo año del 2018 tuvimos dos, la que fuera fundacional y después el segundo simposio, 2019 el tercero, el año pasado que fue en línea, el simposio 4, y hoy que también está haciendo en línea, aprovechando este desarrollo y que el año pasado también fue en línea, poder llegar a más personas, no solamente de la Ciudad de México y del país, sino también principalmente de Latinoamérica y países de habla hispana. Eh, pues damos la bienvenida. Ahorita vamos a poner simplemente un cintillo para que vean que ya está activa la transmisión. De nuevo, solamente es agradecer a ustedes, recordar el trabajo del doctor Germinal Cocho, que ya falleció hace 2 años, y pues este proyecto inició con él, como les mencionaba, en el Instituto de Física en el año 2018, y a partir de ahí se dio paso a esto que estamos construyendo, que se está construyendo gracias a ustedes, los ponentes, las actividades que hemos estado realizando, que es la red de investigación interdisciplinaria en Quiralidad, RIC, y los invitamos a seguir la página, las redes sociales que están en Facebook, en Twitter, y si cualquier cosa que quieran ustedes compartirnos, es bienvenida por los canales que ustedes pueden tener allí de las redes sociales, de nuevo Facebook, Twitter, la página en internet. Bienvenidos. La inauguración entonces va a ser 9:15 con la doctora Sandra Ramírez y les voy a presentar entonces un video simplemente para dar paso a las 9:15 a la inauguración formal del video, del simposio. Bienvenidos entonces y gracias.
No sé si Héctor se quedó en la sala 1. Héctor Durán, ya está ahí.
Ok.
¿Nos vamos otra vez a la sala 1?
Me apareció otro mensaje de sala pequeña. ¿Me cambio o me quedo aquí?
Sí, lo
Yo
mismo a mí.
no entiendo tampoco nada en el momento.
Quédense
Porque,
donde están, en la sala principal,
Ok.
por favor.
Gracias, Martín. Tú nos vas guiando, por favor.
entonces yo digo que leave, no.
No, tú nada,
No,
Tomás.
Ok.
Martín nos va a mover.
Sí, ahorita quédense donde están.
Sí, gracias, Martín.
Sí, lo mismo a mí.
Sandra, ya está saliendo
en el momento.
ya está saliendo Sandra en YouTube.
Hola, buen día. Vamos a dar inicio con las actividades del quinto simposio de la Red de Investigación Interdisciplinaria en Quiralidad. Pues los saludo con mucho gusto, les doy la más cordial bienvenida. Pues estamos muy contentos de esta quinta emisión del Simposio de la Red de Investigación Interdisciplinaria en Quiralidad, nuevamente en un formato completamente digital, por lo que agradezco la participación de las personas que nos están siguiendo a través de YouTube y, por supuesto, pues del apoyo técnico. También saludo con mucho gusto a las personas conferencistas que estaremos escuchando durante la jornada. En esta ocasión, contamos con especialistas que nos acompañan desde Francia, Estados Unidos y diferentes ciudades en México. Entonces, muchas gracias, bienvenidos, buen día para todos. Voy a permitirme compartirles algunas palabras para un poco ponernos en contexto sobre el tema del simposio que nos ocupa hoy. Bien, pues entendemos por quiralidad como una propiedad de asimetría y esta propiedad es relevante en diversas disciplinas científicas como la química, la biología, las matemáticas, la física e inclusive en algunas expresiones artísticas. Uno de los ejemplos más prácticos para explicar el concepto de quiralidad está en la simple observación de nuestras manos. Tenemos una mano derecha y una mano izquierda que entre ellas guardan una relación de imagen especular, Es decir, una es el reflejo de la otra, y además estas son imágenes no superponibles. Yo no puedo hacer coincidir a los dedos de una mano con exactamente los dedos de la otra. Algo semejante sucede con algunas moléculas, y en particular con algunas que son utilizadas por los seres vivos, como los aminoácidos y los azúcares. Estos dos arreglos espaciales que pueden existir para una molécula quiral se denominan enantiómeros y tienen exactamente las mismas propiedades físicas y químicas. La única diferencia entre un par de enantiómeros es la manera en que interactúan con otra u otras moléculas quirales. En términos generales, cada enantiómero puede identificarse como derecho o izquierdo, o más formalmente como el D enantiómero o el L enantiómero. Imaginen ahora que tenemos un par de guantes. Queda claro que el guante derecho única y exclusivamente se ajustará a la mano derecha. No hay manera de que ese guante derecho podamos utilizarlo para colocar ahí nuestra mano izquierda. Los seres vivos terrestres utilizamos solo L aminoácidos y D azúcares para construir nuestras biomoléculas. A esta característica se le identifica como homoquiralidad, lo cual es un hecho que ha llamado la atención desde su definición y descubrimiento y se mantiene como una pregunta abierta en ciencias en espera de una explicación. Justamente durante las conferencias de hoy, escucharemos algunas propuestas de investigación que buscan aportar respuestas al origen de la homoquiralidad, alguna posible explicación de cómo pudo haber ocurrido esto en el escenario de la Tierra primitiva, y más aún, si este fenómeno puede ocurrir en algún otro lugar del universo. Entonces, estas son algunas de las motivaciones que nos llevaron a quienes integramos la red de investigación interdisciplinaria en Quiralidad a promover la ocurrencia de este simposio. Ello nos permite contar con un espacio que favorece la interacción entre las personas interesadas en estos temas y su interrelación, y avanzar en la comprensión sobre esta particularidad del mundo que nos rodea. Me permito recordarles que sus preguntas y comentarios nos los pueden hacer llegar a través del chat de YouTube para que al término de cada conferencia las podamos compartir con el o la conferencista en turno. Nuevamente bienvenidos y me voy a permitir ahora presentar a nuestra primera conferencista. La primera conferencia del programa está a cargo de la doctora Cornelia Meynert, espero haber pronunciado correctamente el apellido. Ella es investigadora adscrita al Institut de Chimie de Nice de la Université Côte d'Azur en Francia. Bonjour, doctor Meynert, bienvenue.
Bonjour.
Les comparto algunos datos de la brillante trayectoria académica de la doctora Meynert. Su investigación está orientada hacia el estudio del origen de moléculas quirales y su detección en partículas de polvo interestelar, cometas, meteoritos o la superficie de algún objeto planetario. Tiene especial interés por los procesos de formación de moléculas orgánicas originados por fotones circularmente polarizados y su evolución en ambientes interestelares. Para ello, hace uso de técnicas analíticas como cromatografía quiral y espectroscopía quiróptica, así como radiación ultravioleta circularmente polarizada proveniente del sincrotrón Soleil. Recibió el premio a la excelencia otorgado por la Université Côte d'Azur en 2018 y en 2019, el premio de joven investigadora 2018 que otorga la Sociedad Francesa de Exobiología y el de joven investigadora 2019 en la División de Química Física de la Sociedad Química de Francia. Y desde 2020 se desempeña como directora de investigación en el Instituto de Química de Niza, en Francia. El título de su conferencia es Why Nature Never Makes Chiral Twins, Insights from Chiroptical Spectroscopy and Extra-terrestrial Sample Analysis. Dear Cornelia, thank you very much for accepting our invitation. We are really honored to have you here. The floor is yours. I will notify you 5 minutes before the end of the 40 minutes you have to develop your topic. Is it okay? The sound, Cornelia?
Yes.
Okay.
I'll try.
Thank you.
Okay.
So please, we are ready to listen to you. Welcome again, Cornelia.
Yes, I'm just trying to hide. This I don't need. I just want my pointer, maybe, where I can have it. Someone can help me. Normally I can find the pointer.
Have the mouse, the little arrow.
This you see?
Yes, it appears.
Okay. Okay. If this is sufficient for you, because I cannot find now the other one. I hide floating meeting controls. Okay. Okay. So then, thank you again. I can start?
Yeah, please.
Okay, so yeah, thank you, Sandra, very much, and all the Mexican community working on chirality, who thought that I would be a good speaker for your topic and even starting your symposium on chirality. And even so, I'm not speaking any Spanish. I was able to follow slightly your introduction. So I heard already that you spoke about what are two enantiomers and that we distinguish between them, and that this is very important in life, and that we call this homochirality, biological homochirality. And so this is actually what I'm working on. And my title, as you can see, is linked to this question of why life is only using one particular enantiomer versus its opposite enantiomer. Even so, as Sandra very nicely explained in Spanish, the two enantiomers would have the same physicochemical properties. So there is no natural explanation or physicochemical explanation why life has chosen one enantiomer out of the two. And now I need to advance my slides here. And this I also try to minimize. I don't need to see me. Okay, and this is exactly the question we are asking in our team, is about the homochirality of life. So here you can see, as Sandra also nicely used her hands to best explain what chiral molecules are about. And I hope that I do not need to introduce more than this chirality, as this is a chirality symposium. Just to recall that in our genetic material, so in the DNA, we use sugar molecules, deoxyribose in the DNA and ribose in the RNA, in the backbone of this genetic material. And those chiral sugars are exclusively used in their right-handed form, so indicated by the little d. And if you look to the proteins, into the monomers of proteins, which are amino acids, all those amino acids in those proteins are of the left-handed configuration. And as already introduced, those enantiomers are equal in energy, in reaction schemes, except in the interaction with other chiral entities, chiral light, chiral molecules. And so the question is why life has chosen the left-handed form for amino acids and the right-handed form for sugars. And we often call this the symmetry is broken, the homochirality of life problem. And starting with the origin of life question started already in the early 19th century, where first organic chemists tried to synthesize organic molecules based on inorganic material. And so here you can see, without going into too much detail, a timeline of first synthesis of organic molecules. And one experiment which was of particular importance for the origin of life research field I'm working currently on is this famous Miller-Urey experiment in the early 50s that for the first time showed that in a very primitive Earth atmosphere, at this time they thought it's a very reducing atmosphere, using methane, ammonia, water, using this very famous spark experiment, where they could form, starting with those inorganic molecules, starting to create organic molecules, amino acids. And so this kick-started this origin of life field, and this idea that organic life, organic material can come from inorganic starting material. So there's both big questions related to this: when, where, and how did life begin? And for sure, as introduced, how life became handed and at which time life became handed. And as already said, one of the first ideas of where life or organic molecules could have been formed was for sure on the early Earth, in the early atmosphere, or later on ideas came about of a primordial soup, that this was very likely the origin of life here on Earth. Later on, other researchers proposed hydrothermal vents. Hydrothermal vents have the advantage of having a pH gradient that can catalyze reactions, so out of equilibrium reactions where you need a lot of energy into the system to create complex chemistries. And there is another big area or in origin scenario, which try to explain that organic molecules are formed in interstellar environments, in molecular clouds, and were brought to the early Earth. At the very beginning, there was a period of early Earth, we call it the heavy bombardment period, where a lot of meteorites fall onto the early Earth and brought with this meteoritic material organic molecules. And this hypothesis, this extraterrestrial delivery, is supported by the analysis of meteorites. We have meteorites that still fall on the Earth. Maybe some of you heard about. Sometimes it's very big in the news if a new meteorite is falling on the Earth. Meteorites can come from asteroids or comets. So each extraterrestrial material that arrives on the surface of Earth is classified to be a meteorite. And then by studying this meteoritic material, we can try to find its original parent body, such as asteroids or comets. And there is a particular class of meteorites that contain organic material. Those are called CM meteorites. And those carbonaceous meteorites have a large fraction of organic material, and if you extract this organic material, a little bit indicated by this image here on the left, if you extract the organic material from those meteorites and analyze the organic content, you can have here find a list of all the diverse classes of organic material compounds that are found in diverse sets of those kind of carbonaceous chondrites. And here on the bottom, you see that also amino acids and sugar molecules important for the origin of life are found in those meteorites. Those organic materials, for sure, are always questioned if this is not contamination from during the entry in the Earth's atmosphere. But most of the time, isotopic measurements are also carried out for those molecules that indicate higher isotopic ratios for the heavier elements, so for deuterium, for example, or carbon-13, which is clearly indicating an interstellar or extraterrestrial origin of those compounds. And so those research on the extraction of organic matter from meteorites is supporting this idea, which is depicted here on the right, that when the early Earth was formed and meteorites during the heavy bombardment hit those, the early Earth, were bringing at the same time organic material. And another particularity of those organic compounds found in meteorites, as for example amino acids, if we carry out an enantioselective analysis, so if we separate the two enantiomeric forms of amino acids that can exist in the right and the left-handed form, you can see here an image of a gas chromatographic analysis from a real meteorite. In this case, it was a Murchison meteorite, one of the most famous and most studied meteorites that we have in our collections. And here you can see always two peaks for each amino acid. So for example, it's the right and the left-handed form of alanine, valine, norvaline, leucine, and so on. And if you clearly look at the two enantiomer forms, you can see that the left-handed form of the amino acid is always a little bit more abundant. The peak is always higher. And this is exactly what we observe not only in this famous Murchison meteorite, but in almost all carbonaceous chondrite, that the amino acids extracted from those stones always carry an excess of the left-handed form. And remember what I said in the beginning, that it's this left-handed form that we carry in our proteins, in all living beings. And so this is why the idea is supported that not only organic material were delivered to the early Earth, but also the selection of the handedness. So why life has chosen this left-handedness is because somehow in space, this selection had been done already before even life could choose. To better understand the formation of those organic molecules, how those molecules can be actually formed in those relatively cold environments in interstellar space. Due to radio observations, we know a lot of the chemistries going on in molecular clouds. And here, if you start on the left side of this slide, you see a kind of dust grain. And those dust grains are quite abundant in molecular clouds in the interstellar medium. So the interstellar medium, if you look up to the sky, you see a lot of stars. And you see an area which is black, so you think there is nothing. So there's only the vacuum, but this is wrong. In the interstellar medium, in the molecular clouds, you do find a lot of dust particles. And on those silicate grains, volatile species such as CO2, water, ammonia, methanol, rather small volatile species, can condense. And because most of the small molecules, because oxygen and hydrogen are the most abundant elements in interstellar environments, water will be formed. So they form ice layers. This is why we often call those kind of layers interstellar ices. And I will use this word further on also in my talk. So interstellar ices are formed around those dust grains. In the interstellar environments, you have certain energies. You have cosmic radiation, you have UV photons from very massive stars that can trigger further chemistries in those interstellar ices, creating radicals. Ions are created that in regions in interstellar space where it can get warmer up to 80 Kelvin, 100 Kelvin, those radicals get mobile, can recombine, and can form more complex organic molecules, such as the amino acids that we can see in meteorites. And those individual dust grains with their ice mantle around would agglomerate and form comets. And so comets are a good body to study those kind of very primitive steps of how complex organic molecules are formed in interstellar space. And this was one of the ideas of this famous Rosetta mission, which recently investigated 67P, this comet, which had the idea to study very pristine material of our solar system. Because here on this image on the right, for those maybe a little bit less familiar with interstellar chemistries, comets in our solar system can be considered as the most primitive bodies that contain information about our solar system when it was formed a billion years ago, because they remain in the outer layers. So very far from the sun. The sun is heating the material, is emitting UV photons. So our solar system after the creation was very much transformed. All the organics, all the material inside was very much modified. And comets are considered, because they stayed in the outer regions, they are considered to remain very primitive. And so to get insights about the very early chemistry, even before our solar system formed. And doing this Rosetta mission, organic molecules such as glycine, so the very simplest amino acid, and phosphorus was detected. And so another support of this idea that complex organic molecules can form in outer space and be delivered by meteorites to the early Earth. So now you saw we can analyze meteorites, we can investigate cometary matter, but those are actually very rare events. And to get a further insight or a more detailed insight in this chemistry of interstellar formation, we perform experiments in the lab to simulate those chemistry in astrophysical ices. And therefore we use a vacuum chamber under vacuum, very low temperature, using gases that we know are out in those environments, such as water, ammonia, and methanol. And we shine UV light at Lyman alpha on them to recreate what I told you just a few slides ago, to build up interstellar ices and trigger their chemistry. And here on the right, you have the image of the real chamber that is in the laboratory at the moment in Marseille. With colleagues, we work very closely together to better understand this chemistry. And during the last 10 years, we were able, in those interstellar ices, these primitive ices that we create in the laboratory, we could find sugar molecules such as ribose. Ribose, remember, is very important for the RNA, so one of the key sugar building block for the genetic material, which we found in those simulated interstellar ices. Nucleobases have been detected in those primitive ices by a Japanese team in 2019. We also detected a lot of amino acids in those samples, and very recently, in a collaboration with Ralf Kaiser from the University of Hawaii, we were also interested if precursors for lipids, phosphorus lipids that contain phosphorus as their head group, if those molecules can also form in those interstellar ices. And this we have shown very recently by detecting methyl phosphate, methylphosphonic acid, so alkylated phosphoric compounds, all in those very primitive ices, very primitive reactions, and you can form very easily all those complex molecules. Coming now back to the first question of chirality, how those asymmetry that we also see in the meteorites. Now, remember, there is a slight excess for the left-handed form in the amino acids, how this excess can be created. And to induce asymmetry, we know that there are several different kind of a series mechanism that can lead to a chiral selection. So you can have crystallization, you can have selective adsorption on chiral minerals such as quartz. Quartz, you can have a D quartz and a L quartz, so initially a chiral system. But those processes are often called random processes because you can find quartz as a D and a L quartz, whereas here on the right, you find more deterministic processes. And in the follow-up, I will focus most of my talk now on the circular polarized light interaction. But before doing this, I just would like to highlight that we very recently started to have a look on this, onto this interaction of chiral material and chiral crystals. And I just want to highlight that this is a very recent project of our team. And we are really in the beginning to try to understand, because the mineral surface is very complex. You can have chiral surfaces on an achiral crystal. So I think this is something we will definitely work in the future on. And if you are interested in this or work on this, I would be very happy later to discuss with you on this research branch. However, one of our main idea or research that we are looking at the moment, how this L excess in those meteoritic amino acids could have originated, is by circular polarized light. Circular polarized light is by itself a chiral entity indicated here. You can find circular polarized light in its right and its left-handed form. So the electric field vector rotates clockwise or anti-clockwise in the direction of propagation of the light, so creating left or right circular polarized light. And this particular light, because it's chiral, is interacting differently with enantiomers. And this light has been detected in molecular clouds. So in those clouds where those interstellar ices are formed, which I just showed you before. And so the idea is that this interstellar circular polarized light would have acted with the organic material in those ices and created an excess in the left-handed form. And to understand the interaction of this circular polarized light with chiral molecules, we investigate their circular dichroism. The circular dichroism is exactly this. It describes the differential absorption of an enantiomer versus the incoming left and right circular polarized light, to understand at which energy an enantiomer can discriminate, or the incoming light can discriminate between the two enantiomers. And this we have done in our team together with Uwe Meyer-Henrich since many years, that we recorded CD and anisotropy spectra. And maybe without going into too much detail, here you can see the anisotropy spectra, which is a derivative of the circular dichroism spectra, which is dividing the circular dichroism by the overall net absorption to get in net information of what asymmetric photolysis could induce into chiral mixtures. And so here you have the anisotropy factor plotted over the energy of this incoming light. In blue, you see the left-handed form of alanine. In red, you have the opposite enantiomer, the D, and you see, depending on the energy, the anisotropy factor is changing and has some optima. So you would expect that the enantiomers at 200 nanometer have a different absorption, or they do have a different absorption at this energy. And those spectra are helping us to predict the inducible sign of an enantiomeric excess in asymmetric photolysis, which is plotted here on the right-hand side. So we use an equation that where we use the anisotropy factor. The C is a photolysis rate, how long we drive asymmetric photolysis reaction. And we can predict based on our spectra, what is the enantiomeric excess, so the imbalance that we can create in an initially racemic mixture of equally left and right-handed form. We can also see at which wavelengths we could induce the maximum. And those spectra we have in the past recorded for A- alcohol acid, for a huge number of chiral organic molecules that are also found in meteorites. And those anisotropy spectra, those data, we also try to correlate with the enantiomeric excess found in meteorites. And to confirm that our anisotropy spectra are giving us a real result and the real impact of circular polarized light, what we have done in the past is that we have started with a racemic mixture, so 50-50 left and right-handed enantiomers of, in this case, alanine is the simplest amino acids. And we have, based on the anisotropy spectra, irradiated at 200 nanometer, where we saw the biggest discrimination between the two helicities of the light. And when we irradiate an initially mixture of 50-50, so racemic mixture with left circular polarized light, we create an excess of the left-handed form of alanine. If we now switch the helicity to right-handed circular polarized light, we get an excess of the opposite enantiomer. So exactly as predicted by our anisotropy spectra, we carried out this asymmetric photolysis experiments, where for the first time we could show that this asymmetric interaction with the circular polarized light is wavelength dependent and helicity dependent. Then remember, I showed you this ice chamber where we create those interstellar ices in the laboratory, where in those ices we see amino acids. Our idea was now, if we would replace the UV lamp, the Lyman alpha, with circular polarized light, could we still form amino acids, and would they be formed in different ratios? And this is exactly what we obtained when we created those interstellar ices containing amino acid with left circular polarized light. We could see in excess of the left-handed form. When we created those ices with the opposite enantiomer, so of these photons with right circular polarized light, we created an excess in the D enantiomer, in situ in those ices. Now, all those studies that I have showed you, we have carried out in the solid state, because we thought we focus first on the interstellar dust grains. What happens on the dust grains? During the Rosetta mission, glycine had been found in the gas phase. So we were wondering if this interaction between the circular polarized light and amino acid can also be achieved in the gas phase. So we have built a gas chamber that we attached to the synchrotron, where we measure the circular dichroism and anisotropy spectra. And so we sublimated, we put different kind of amino acids into the gas phase, and again recorded the anisotropy factor versus the energy of the incoming photons. And here, as an example, I show you the anisotropy spectra of alanine. And again, we can see that depending on the energy, you have some optimum, some maxima in this in the anisotropy, where you are able to achieve a high enantiomeric excess by circular polarized light. And this study we have also for sure not only carried out for alanine, but for a different kind of amino acids in the gas phase. And for those of you who are a little bit more interested in physicochemistry, working in the gas phase also allowed us to do some thermodynamic calculations and to attribute which conformer actually is responsible for the big anisotropy value that we experimentally measured. So we were able to deduce that in this case, it's a rather high energetic conformer 4. And if someone is more interested in this work, I would also be happy to discuss with you further on this. However, what would happen in the origin of life community while we attend several conferences a year over the last years? We always heard the argument, yeah, but if you come with your monomers, your amino acids to Earth, how they can polymerize? Because amino acids in liquid solution would not polymerize easily. And so recent studies have shown that when you have a cycle, a wet and dry cycle on the early Earth, either due to night and day cycles, tides, so where you have an income flux of water, drying out of water, in those kind of cycles that are very popular in the origin of life domain at the moment, they used amino acids and hydroxycarboxylic acids, and they found that if they do this kind of wet and dry cycles, they form dipeptides. So you have always a unit of an amino acids, of an acid. And if you do this wet and dry cycles more than 10, 20 times, you replace by time the hydroxy acid and form a peptide. And this could be a possibility to form longer peptides on the early Earth. We knew from the literature that lactic acid, so the most primitive carboxylic acid, has also been found in Murchison. So we were wondering if there could be a possible link between those hydroxycarboxylic acids and amino acids in interstellar environments, if they could have both get an enantiomeric excess interacting with circular polarized light. And for this, we again carried out anisotropy spectra, and this was led by Jana, a postdoc in our laboratory, who recorded the spectra of hydroxycarboxylic acid and compared them to the amino acid spectra. And what we could see is that they always have the same dominant band. And the conclusion of this study, to maybe speed up a little bit, the conclusion of this study was that if either hydroxycarboxylic acids or amino acids or both would have interacted with circular polarized light, they would have get the same handedness. So both could have arrived on early Earth with a small initial excess of the left-handed form, which could have been amplified during the polymerization reaction on early Earth. So this was a quite confirming result for us in this aspect of more pre-body chemistry on early Earth. And maybe to summarize what we have learned in the past about this scenario, whether circular polarized light could have been at the origin of our left-handed amino acids, what we have see with our experiment in the past is that for sure the enantiomeric excess that you can create is depending on the polarization and the energy of this light, but that depending on the physical state, so I showed you the gas phase, I showed you a solid state, amino acids have different kind of anisotropy spectra. So the interaction with circular photons is depending on the pH, the complexation, the physical state, and all those can influence the interaction. And what I haven't emphasized at the moment was that when you remember what I have, or when you try to have followed me in the last minutes, is that when we carried out those asymmetric photolysis experiments, we did this at a given wavelength, because at a given energy, because our anisotropy spectra are telling us at a given energy, we would expect a higher discriminating effect of circular polarized light. But in space, circular polarized light would be polychromatic, so it would not be emitted at one given energy. And additionally, what you can see here, this is a massive star, and the stellar outflow, the molecular outflow of the star. In this outflow, the circular polarized light would be right-handed, versus on the opposite lobe of this molecular outflow, it would be left-handed. And so we ask ourselves, can we somehow deduce from our data that we have which handedness the circular polarized light would have had when our solar system formed? And for this, we saw a recent discovery of propylene oxide. Propylene oxide as such is a chiral molecule, but not that important for pre-body chemistry. However, propylene oxide was the first chiral molecule directly detected in molecular environments. It has also been detected in the Murchison meteorite, and researchers have separated the two enantiomers and have found an excess for the right-handed enantiomer of propylene oxide in this Murchison meteorite. So now you can imagine what we have done is we wanted to know the interaction of propylene oxide with circular polarized light. So we recorded again our CD spectra. So here you have the absorption spectra in black. In blue, you have the CD spectra, but maybe since I most of the time talked about anisotropy spectra, I will go immediately to this image where you can again see the different absorption bands or anisotropy bands depending of the energy. We also again did some calculations. And the idea of this study was again, together with Jana in our team, is that we wanted to know what would happen if we would have broadband circular polarized light. So more realistic circular polarized light, which we would assume to be present in interstellar environments. So we weighted our spectra, our anisotropy spectra, and wanted to see what is the net effect of broadband circular polarized light. And we wanted to compare this with the 10% of the R excess found in propylene oxide in meteorites. And so what we could see is that, yes, it is possible that broadband circular polarized light is inducing a net enantiomeric excess. And if we want to reach an excess in the right form of propylene oxide, in the R stereoisomer, we would require left circular polarized light. And this study has been recently accepted. And this is the first time that our team is trying to predict that when the first organic molecules have been formed, that may have been interacted with circular polarized light and delivered with meteorites to our early Earth, that the light required would have been of left-handedness, which for sure we would need to confirm now in the future. And maybe as the last chapter of my talk today, I talked a lot about amino acids. I showed you in the very beginning of my talk that in those interstellar ices that we form in the laboratory, we recently also saw sugar molecules. In meteorites, also very recently, ribose, arabinose have also been detected. And the analysis of sugar molecules is very difficult. So for those of you who are analytical chemists or organic chemists, know that the analysis of sugar molecules is much more complex than the one for amino acids. And our current goal in our team is to develop an integrative workflow where we extract the organic part of meteorites, fractionate the amino and sugar content, do derivatization, because we do a lot of gas chromatography analyses, and because amino acids and sugar molecules are unfortunately not volatile, we need to transfer them to make them more volatile, and this we do by the so-called derivatization, different kind of derivatization, to finally do GC-GCMS analysis, what is our main analytical tool in our laboratory. And this is was first developed by one of my PhD students, Raphael, and Vanessa is now continuing this work to carefully develop all those tools and steps, and to be as less as contaminated as possible. Because imagine you have real meteorite samples, you want to make sure that the amino acids that you afterwards detect in your last step are not coming from any contamination. So this is why it's a very tedious work, and I'm very thankful for my students who do not give up to develop these protocols. And so another PhD student that I need to highlight is Adrien, who was responsible to find a way of detecting and analyzing those sugar molecules, because as I said already, that sugar molecules are very difficult to analyze because they do this intramolecular ring closure. And this they can do by two ways. They can form 5-membered rings or 6-member rings. And as an example, if you see here, the ribose, you can form the 6-member ring, the pyranose form, but depending on the OH group at the carbon 1 position in the ring, which can be in the alpha or beta position, you form already 2 forms. Then you form 2 other forms for the furanose form, and you have the open form in the mixture. And this is 5 forms for D-ribose. If you now have a mixture of D and L, you would have 10 peaks in your chromatogram. So his goal was to find derivatization methods to limit the number of stereoisomers, increase the resolution, to be able to calculate very reliable any enantiomic excess in extraterrestrial matter. And this is, without going into details, is a work that we currently try to write up on this sugar analysis, working up analytical protocols to reliable determine the EE in extraterrestrial samples. And this is exactly our next goal in our team, is to look after developing carefully those analytical methods for the enantioselective sugar and amino acid analysis. There are 2 missions currently ongoing. The Hayabusa 2 and OSIRIS-REx missions are 2 asteroid sample return missions. Hayabusa 2 has already successfully returned pristine sample from the asteroid. OSIRIS-REx will bring his samples, its collected samples back next year. And you can imagine that the advantage of those samples is that since they haven't entered the Earth's atmospheres, as meteorites have done, we consider them as quite free of contamination. So they are currently stored very carefully in contamination-free environments. And we are now in the situation to be able to have an analytical method ready to look into the chirality in those very, very pristine material and non-contaminated material. And with this, I would like to give you some future trends. So I explained you already the complexity of the interaction of chiral molecules with circular polarized light, and a direction in which our team is now going is that we want to better understand what is the effect of this polychromatic circular polarized light, so broadband circular polarized light, onto chiral molecules, not only amino acids, but other chiral molecules that are identified in extraterrestrial material, such as meteorites, to get an understanding if circular polarized light was really at the origin of the detected enantiomeric excess in those compounds. For this, we will look for those chiral biosignatures in meteorites and asteroids and compare with our anisotropy spectra, but also with the experiments that we carry out studying the interaction of circular polarized light with chiral molecules. And something I haven't had the time, but something we would like to do in the very near future is to look into the chiral amplification, because the enantiomeric excess that circular polarized light can induce is rather small, so a few %. But the question is how life, or how doing the processes of the pre-Baltic chemistry on early Earth, how those small enantiomeric excesses could have been amplified. And for sure, as highlighted a little bit very quickly on our new branch of science looking into the effect of chiral minerals, we are for sure open for alternative origins for biomolecular homochirality. At the moment, the circular polarized light scenario is very promising because circular polarized light is detected in space. We find enantiomeric excess in meteoritic amino acids, so that there is a strong evidence somehow that this enantiomeric excess could have been originated in interstellar environments. But however, we are more than open to discuss alternative scenarios. And with this, I would like to thank again my team that I have in Nice, so my former PhD students, Adrien and Raphael, who very recently defended successfully their PhD. And I have Vanessa Leva as a PhD student who is working on the meteorite analysis in my laboratory. For sure, Professor Meyer-Henrich, who recruited me first and brought me into this very fascinating topic of biological homochirality. Our co-workers at the University of Aarhus, with whom we do all the circular dichrism and isotropy measurements. Louis Dondecourt, with whom we do the ICE experiments. Laurent Nahon from the Soleil synchrotron, where we perform those irradiation experiments using circular polarized light. And very recently, I have started to collaborate with Ralf Kaiser also on those ICE experiments. And for sure, all the funding agencies required for this fundamental research question, because I will not save anyone's life with this research, but we try to answer a very fundamental question. Maybe most of us have asked themselves already where we did originate, how life originated, and maybe is there life somewhere else in the universe? And if you found this topic now so appealing and want to join or meet the astrobiology community, I just would like to highlight 3 major conferences coming up next year. Maybe for the people in Mexico, the ESOL conference, because this will be in Quito, Ecuador. Maybe this will be the closest for you. If we have any European people attending the conference today, there will be a conference organized in Spain at the Canary Island by the European Astrobiology Institute next year in May. And with this, I thank you for your attention, and I'm glad to take any questions from you.
Thank you very much, Cornelia. It has been a wonderful talk with a lot of very interesting results, and of course, perspectives. Thank you very much.
Welcome.
And yes, we have some questions. Thomas asks, how to explain a chiral bias of the circularly polarized light in the universe? Is parity violation involved?
No, for the photons not. The photons are detected, so there is a detection, this astronomical observation of circular polarized photons, of left and right-handed photons, and there are models to predict how the circular polarized light can be explained. And because around those massive stars that have a magnetic field, this magnetic field is aligning dust particles around the stars. And on those dust particles, the emitted light, unpolarized light of the massive center star is scattered. And this scattering creates polarization. And so this is currently simulations going on to explain the observed infrared circular polarization of the photons in molecular clouds. Nothing involved with the parity violation energy difference.
Okay, thank you. From YouTube, we have another question. Quetzal asks, can chiral asymmetry allow to facilitate a definition for life? Can it be something that we can use to distinguish something alive and something that is not? Or is it just a genetic property of the universe?
This is a very, very good question. And this is actually what is now very much promoted in any space mission. So there are a lot of space missions driven by the question, is there life somewhere else in our solar system or on exoplanets? If you followed Mars missions that look for life, because we know, as easily shown by the Miller-Urey experiment or by the interstellar ice experiments that we do, that abiotic processes can easily create organic material. So this is not a proof of life. So we need somehow stronger arguments, stronger signatures that really can indicate if there is current life, if there has been life. And chirality is exactly this kind of a signature that missions such as the Rosetta mission, several Mars missions are looking for chirality, because only life is homochiral. If you have abiotic processes, you have both enantiomers. Even now, in abiotic process, the interaction with circular polarized light will give you a small excess, but not homochirality. So there is something needed to create homochirality, and this is life. And this is why homochirality is clearly linked to life. We do not know at which stages in the evolution of living system everything became homochiral, but there are a lot of biochemistry data showing also if you replace in the genetic material or in proteins, if you change the configuration of one enantiomer, the folding of a protein becomes totally different. So the efficiency of the enzyme activity can be totally decreased. So homochirality on a biological level is very fundamental. I hope that this answered your question.
Yeah, very, very well. Very nice answer. Thank you. Thomas again, and I think it is related to the previous question. It says, how is about amplification mechanisms?
Yes, so this is, there are different ones. So one amplification mechanism I would like to study in the past is this polymerization, because at some point the monomers had to polymerize. And in my opinion, this is a good starting point to look at. There are asymmetric catalysis showing that you can amplify small excesses. There was this famous demonstration of the SOI reaction that showed that autocatalytic reactions are able to drive a system from a very tiny excess to homochiral state. But at the moment, prebiotic chemists have difficulties to find a system that could have been applied on prebiotic Earth. So this asymmetric amplification in this organic reaction network could, in a prebiotic setting, not be proven at the moment. So this is for sure also a possibility. But since at one point we need polymers, my guess is that it was at this state that either template-directed polymerization could have drives the amplification, or simple polymerization, as shown in those wet and dry cycles, could have created a selection of one-handedness.
Okay, thank you. Alejandro Heredia asks, how is the interaction of the chiral molecules with the column, with the selector? I think it refers to your experiments.
Yes, so this is a technical analytical question. So what we do in our gas chromatography analyses, we use a chiral column. And this is the chiral column can therefore discriminate between the two enantiomers. So we have one enantiomer eluting first, whereas the second enantiomer eluting later, because it's interacting more strongly with my chiral selector. For the amino acids, I can tell you we use a chiral selector having valine inside, so an amino acid, either as L-valine or D, so left or right valine. So for sure, it's able to distinguish between the two handedness. For the sugars, we use cyclodextrin, so cages of glucose, which is also chiral and also able to distinguish between the two sugar enantiomers.
Okay, thank you. Another question from Hector Vasquez. If we consider that in the universe at different times, decisions about a certain preference of chirality have been taken, what physical forces could be involved in these decisions?
Yeah, what we currently believe or work on is the circular polarized light. And this is just by chance that our solar system, I don't know if maybe I was very quick on this. If I go back, you have to imagine that our solar system has this size. So it would have only see one-handedness of the circular polarized light. This is why in the study of this propylene oxide, we were somehow interested, but what was the handedness of this light? Was it now left or right? Because due to the symmetry in the universe and the process to create the circular polarized light, you would have one side of the massive star being left-handed circular polarized light, and in the opposite lobe, you would have the opposite helicity, except that our solar system, again, is very small compared to these regions where you find either left or right-handed photons, and so that we would have been only impacted by one-handedness. But this is by chance that if we would have been formed on this side, we would have, if we believe that the circular polarized light scenario was at the origin, then we would have been all with the opposite handedness, because this also biologists have shown proteins completely composed of D enantiomers would also be fine. The only requirement is it has to be homochiral.
That's it. Okay, I missed a question from Thomas, but I think it fits well here. Does it mean that the universe is intrinsically asymmetric?
I wouldn't say this, that it's asymmetric, because if we think now about in terms of the circular polarized light, there is a symmetry. A circular polarized light, you will find always left and right. So there is no, in this circular polarized light itself, if you average the universe, you would find the same amount of left and right-handedness. So this is also why researchers sometimes say that if we could travel very far away, it could be possible that we could find life with the opposite enantiomers.
Excellent. Thank you very much. Well, it has been a very nice talk, a very nice discussion. Also, thank you everybody for your questions. I think it's time that we let Cornelia to rest a little. Thank you very much, Cornelia. I hope you can be with us for the rest of the journey. We will be interacting in a little more minutes. And I have a message from the technical equipment that a couple of minutes are needed for the next transmission. So please tell me if we stop here, if we could, or what do we do? Somebody?
I just see some thank you in the YouTube. So thank you very much. It was also a very pleasure to attend and have this very interesting discussions with you also. So, and if someone had a question and not the chance to ask, please contact me, read our papers, get in touch with us. We'll be happy to exchange. So, bye-bye.
Thank you. Ok, bueno, nos detenemos aquí. Gracias. Me indican, por favor.